At some point, Einstein was not satisfied by the fact that to derive his field equations, he had to hypothesize that the potential tends to zero towards infinity, and that the universe is spatially infinite. And we derived Einstein's field equations written in the following form. Let me remind this: G mu nu equal to minus k times T mu nu minus 1/2 G mu nu times T, and G mu nu is equal to minus derivative with respect to x alpha, Christoffel symbol mu nu alpha, that Einstein writes using this notation, plus Christoffel symbol mu alpha beta times Christoffel nu beta alpha, plus, then here we have the second derivative of the natural logarithm of the square root of minus the determinant of the metric tensor with respect to x mu, with respect to x nu, and then we have minus Christoffel mu nu alpha, derivative of the natural log of square root of minus g with respect to x alpha. Now, Einstein wanted to add a term to this equation here, a small correction to this equation. So he wanted to rewrite that equation like this: G mu nu minus lambda, which is a constant, times the metric tensor G mu nu equal to minus k times T mu nu minus 1/2 G mu nu T, where lambda is sufficiently small. Now we will have to investigate deeper, and we will find the meaning of this lambda and why it's important. First and foremost, we ask the question, is this a legitimate correction to the field equations? Well, the answer is yes, because the equation is still covariant, as you can see, because we have simply added a constant which multiplies a tensor. So we still get covariant equations. And also, the law of conservation of energy is still preserved, as the covariant derivative of the metric tensor is zero. So we still have the law of conservation. That's still valid. Now let's try to understand what is lambda and how to calculate it. The most important fact that we draw from experience as to the distribution of matter is that the relative velocities of the stars are very small as compared with the velocity of light. So Einstein bases his reasoning on the following assumption. There exists a frame of reference relative to which matter may be looked upon as being permanently at rest. With respect to this frame of reference, the energy tensor has only one non-zero component, or maybe I should say only one non-negligible component, which is T44 equal to rho c squared. And if we consider a set of units such that c is equal to 1, then of course this is equal to rho. Einstein then hypothesizes that G44 is equal to 1 and G4J is equal to 0, where J can be either 1, 2, or 3. Whereas for the spatial coordinates of the metric tensor, he assumes spherical symmetry. We have to derive the spatial part of the metric tensor, and we arrive at the result, for example, in the following way. We start from a Euclidean space of 4 dimensions, and I will call the coordinates xi1, xi2, xi3, xi4, and if they are Euclidean, as I said, the element d sigma squared will be equal to d xi1 squared plus d xi2 squared plus d xi3 squared plus d xi4 squared. Then in this space we consider also the hypersphere, so we will consider this function r squared equal to xi1 squared plus xi2 squared plus xi3 squared plus xi4 squared. So this is a hypersphere because we are in 4 dimensions, and r is the radius of such sphere. From this, we can also find that xi4 can be written as the square root of r squared minus xi1 squared plus xi2 squared plus xi3 squared, and we can call the sum of these squares just rho squared. And from here we find d xi4 equal to minus xi1 d xi1 plus xi2 d xi2 plus xi3 d xi3, and then we divide this by the square root of r squared minus rho squared, like this. In principle, we also have a plus or minus sign here, but this is not important because we will now substitute this differential here in this expression for d sigma squared. So since we have squares, plus or minus signs are not important. So in here, if we make this substitution, we get d sigma squared equal to d xi1 squared plus d xi2 squared plus d xi3 squared. Then we get plus. We can rewrite d xi4 squared from here, and you simply get xi1 squared d xi1 squared plus xi2 squared d xi2 squared plus xi3 squared d xi3 squared plus 2 xi1 xi2 d xi1 d xi2 plus 2 xi1 xi3 d xi1 d xi3 plus 2 xi2 xi3 d xi2 d xi3, and we multiply this bracket here by 1 over r squared minus rho squared, like this. So we can rewrite this element d sigma squared like this. We sum over I and over j, and then here we have gamma ij d xi I d xi j, and gamma ij is simply this matrix delta ij, the Kronecker delta or the identity matrix, plus xi I, xi j, and then we divide by r squared minus rho squared. These two together will give me this expression if you just check. So in 4-dimensional space, the g mu nu, if we assume spherical symmetry, can be written like this. We have, remember this assumption, g4i equal to 0, g44 equal to 1, and then we get gij equal to minus, we have to change the sign, of course, according to the metric, and then we have delta ij plus xi xj divided by r squared minus rho squared. So in this case, we have the coordinates x1, x2, x3, and x4. And I and j here can be 1, 2, 3. Remember that. Now we want to write the field equations at one particular point, because the field equations should be satisfied at any point, but we will choose the point x1 equals x2 equals x3 equals x4 equal to 0. And also in this case, rho is equal to the square root of x1 squared plus x2 squared plus x3 squared. And furthermore, at this point, at this particular point, x1 equal to x2 equal to x3 equal to x4 equal to 0, we have that the derivative of g for alpha with respect to x beta is equal to 0, where alpha can be 1, 2, 3, and 4, and beta can also be 1, 2, 3, and 4. Then we get the derivative of gij with respect to x4 is also equal to 0 if you check the expression for the metric tensor, and I and j here can be 1, 2, and 3, but the derivative with respect to x4 is 0 also if we have g alpha beta here actually, because g4 alpha or g44, they are constant. So if we take the derivative, of course, is still equal to 0, but even if we take gij, where I is equal to 1, 2, and 3, and j is equal to 1, 2, or 3, this derivative with respect to x4 is equal to 0. Then we also have derivative of gij with respect to xk is equal to 0 at the point x1 equal to x2 equal to x3 equal to x4 equal to 0. Why is this? Well, if you take the derivative of the gij here, you have this part, of course, because this first part is constant. So if you take this derivative here, for example, the derivative of gij with respect to xi, of course, the derivative will be xj divided by r squared minus rho squared, and then you also have to remember that rho depends on x1, x2, x3. So you might have another term. But when you set x1 equal to x2 equal to x3 equal to x4 equal to 0, the derivative here of this term will still be 0. It's easy to find out, right? The only non-zero derivative here is the second derivative, because when we take two derivatives here, for example, we will get 1. We might get 1, right? If we take the derivative of this term with respect to xi and then with respect to xj, here you might get 1. And when you evaluate this function at x1 equal to x2 equal to x3 equal to x4 equal to 0, from here you will get 1 over r squared. Then, of course, as I said earlier, you can also take the derivatives of this term, but if you take the derivatives of this term, there will still be a factor here, xi, xj. So when you set this equal to 0, you will get 0 contribution from that part. So what I said here can be summarized with just one equation, and the equation is this: del squared gij with respect to xi with respect to xj, this will be equal to minus 1 over r squared when x1 is equal to 0, x2 is equal to 0, x3 is equal to 0, and x4 is equal to 0. So let's rewrite g mu nu. G mu nu, remember the expression, it is minus derivative with respect to x alpha of mu nu alpha, Christoffel symbol, plus Christoffel mu alpha beta times mu beta alpha plus second derivative of the natural log of the square root of minus g with respect to x mu with respect to x nu, and you also have another term which is minus Christoffel mu nu alpha derivative of the natural log of the square root of minus g with respect to x alpha. But according to the assumptions that we have made, this term here will be 0 and also this one. Why? Because when you set x1 equal to x2 equal to x3 equal to x4 equal to 0, you will get 0 contribution from the considerations that we have made above, because if you consider the Christoffel symbols, you know that you have first order derivatives of the metric tensor, right? But when you consider this point up here, these derivatives will be 0. So this one will give 0 contribution, but also this one. It's easy to see. So we are left with only this term, and this term. Now let's consider this first term. Let's consider d with respect to x alpha, Christoffel symbol mu nu alpha, and this is equal to the derivative with respect to x alpha of g alpha tau divided by 2. Then we multiply this by dg tau mu with respect to x nu plus dg tau nu with respect to x mu minus dg mu nu with respect to x tau. Also, let me tell you that this derivative here will only be applied to these terms. Why? Well, because if we apply this derivative to the inverse of the metric tensor, then we will be left with first order derivatives here, but when we set x1 equal to x2 equal to x3 equal to x4 equal to 0, that will give a zero contribution. So the only non-zero contribution can come only from these terms when we take the derivative of those terms. So let's consider, for example, let me do it here, the derivative with respect to x alpha of, let's assume that mu and nu are equal to 4, so we have 4 alpha, and here we have g alpha tau divided by 2, and here we get twice partial derivative of g tau 4 with respect to x alpha and x4 minus dg44 with respect to x tau. But this term here is equal to 0 because g44 is equal to 1. And also this term here is equal to 0 because we have to take the derivative with respect to x4, but that is 0. So this term here is 0. And also let's consider the second derivative of the natural log of the square root of minus g with respect to x mu with respect to x nu. So I'm considering this term here. This derivative can be written like this. It is the derivative with respect to x mu, and then we get 1 over square root of minus g, derivative of the square root of minus g with respect to x nu is equal to derivative with respect to x mu of 1 over 2 g, derivative of g with respect to x nu. But this can also be written like this, derivative with respect to x mu, and we know how to write 1 over g times the derivative of g with respect to x nu according to the rules that we have found in tensor calculus. This can be written as g alpha beta with upper indices divided by 2 derivative of g alpha beta with respect to x nu, and the only non-zero terms are g alpha beta divided by 2 times the second derivative of g alpha beta with respect to x mu with respect to x nu. Now it's easy to check that this term here can be non-zero, and remember this equation here that we have found earlier. So it's easy to check that when you set, remember that you have to set x1 equal to x2 equal to x3 equal to x4 equal to 0. So the inverse of the metric tensor will be equal to the usual matrix minus 1, minus 1, minus 1, 1 on the diagonal, and then we have zeros out of the diagonal. So here we get minus 1 over 2r squared if mu is equal to nu and they are both not equal to 4, and we get 0 otherwise. For mu equal to nu equal to 4, we have g mu nu equal to 0. So the equation that we have, the field equation, will become minus lambda multiplied by 1 because g44 is equal to 1, which is equal to minus k times t44, which is just rho. Remember that c is equal to 1 according to our units, minus 1/2 times t, but t is also equal to rho. So we get from this equation minus lambda equal to minus k rho over 2. Now let's consider other indices for the field equations. And let's consider minus the derivative with respect to xk of Christoffel ijk, and this is equal to minus derivative with respect to xk of gkn over 2, derivative of g and I over dxj plus dg and j with respect to xi minus derivative of gij with respect to xn, and this is equal to, remember that we have to consider only derivatives of these quantities, because if we consider the derivative of this, we will get a zero contribution when we set x1 equal to x2 equal to x3 equal to x4 equal to 0. So here we get minus g and n, so I can replace k with n. K and n should be equal, because otherwise we still get a zero contribution. Because when we set x1 equal to x2 equal to x3 equal to x4 equal to 0, this will become diagonal. So we might as well consider k equal to n. So we have minus g and n over 2. Then we get d squared g and I with respect to xn with respect to xj plus d squared g and j with respect to xn with respect to xi minus d squared gij with respect to x squared n. And here you will get 0 if I is not equal to j, and also if one of them or both of them are equal to 4, and you will get minus 1 over 2r squared if I is equal to j. The field equations for I equal to j and I and j are not equal to 4 become minus 1 over 2r squared, and this comes from the equation that we have just derived. So this is equal to minus derivative with respect to xk of Christoffel ijk. Then we also get another minus 1 over 2r squared, and this term here comes from the second derivative of natural log square root of minus g with respect to xi and with respect to xj. Then we get minus lambda times minus 1. This comes from gij, where I is equal to j, equal to 0, because on the right we have the energy components of matter. So all in all, we get that lambda should be equal to 1 over r squared, and also lambda equal to k rho over 2. And from these two equations, we also get that rho should be equal to 2 over k, 1 over r squared. So we get rho proportional to 1 over r squared, which means that the larger the universe, the smaller the density. And notice that if lambda were equal to 0, these two equations could not be satisfied. Einstein introduced this term, lambda, in order to allow of the possibility that the universe might be finite, and r is indeed the radius of the universe, and also that the density rho can be non-zero when we move towards infinity.